All right, so question 8 asks you to explain the symmetry and sequential models of allostery. Make sure to find the T in the R state. How does oxygen binding cause the T to R state shift? All right, so for this one, we'll start off by defining the T state and the R state. So the T state is the tense state, which binds oxygen weakly. The R state is the relaxed state, which binds oxygen tightly. All right, now the difference between the symmetry and sequential models are that in the symmetry model, all the subunits have to either be in the T state or the R state. All right, you can't have 3 subunits in the T and 1 in the R. You can't have 3 in the R and 1 in the T. You can't have 2 and 2. They all either have a choice of being in the T state or the R state, and there is no in between. Right, that is for the symmetry model. All right, for the sequential model, the subunits now undergo kind of gradual changes from the T state to the R state. So they have the option of being in the pure T state, in a T-like state, in an R-like state, and in addition, all the subunits can basically be in slightly different conformations. So you can have subunits in a more T-like state, others in a more R-like state. Right? That is the sequential model. All right. Now, this kind of so that's basically the difference between them. So now, how does oxygen binding actually cause this shift from the T to the R state? All right. Well, what's happening here? All right. So there's kind of the chemical reason why the T to R state shift is happening, and there's also a thermodynamic reason. So I'll go through both of those. So the chemical reason why it's happening, all right, has to deal with what's causing the conformational change. All right. So normally in the T state of hemoglobin, all right, the iron in the heme is basically up out of the plane of the rest of the heme. So the heme is actually bent. All right, and below the heme, basically there's a histidine down here. All right, this histidine is kind of pulled up along with the iron because it's lying outside the plane of the heme. Now, when oxygen comes in and binds to the iron, all right, this causes a movement of the iron back into the plane of the ring. So the ring is basically flattening out. And as a result, this histidine also gets moved in a downward direction, downward and somewhat to the side, I should say also. But this histidine is not by itself. It is a part of a large alpha helix. All right, so that whole helix of the protein now undergoes a movement. All right, and this helix then propagates this conformational change to an adjacent subunit. So basically the movement of this helix downward is then causing amino acids over here on the other protein that were normally interacting with it to also undergo corresponding conformational changes. All right, so as a result of a conformational change, or a result of ligand binding here to the T state, this causes conformational changes that can get communicated over to the other subunits. And these other subunits now undergo conformational changes that cause them to shift towards the R state. All right, so that's the chemical reason. Now, what about the thermodynamic reason? Well, we're going to look at the symmetry model. So in the symmetry model for allostery, right, we basically have 4 T subunits, and they can all either be in the T state or in the R state. They have a choice of being either or. As I said before in the symmetry model, we can't have mixtures of different types of subunits. Now, either one of these is capable of binding an oxygen. So I'm going to have the T state bind 1 oxygen here, or the R state bind 1 oxygen, and we're going to draw this kind of moving in the downward direction. And what we're going to create here is a thermodynamic box. All right, so when we bind oxygen to the T state, we end up with our 4 T subunits with a single oxygen bound. It's a complex. When we bind it to the R state, we end up with our 4 R subunits with 1 oxygen bound. All right, and these 2 states here with the T bound to the oxygen or the R bound to the oxygen, they can interconvert between T state and R state as well. All right, now one of the things that we said early on when we defined the T state and the R state, all right, we said that the R state binds oxygen more tightly than the T state. All right, so the equilibrium constants here, all right, Please note that I'm talking about association constants here, not dissociation, because the way I'm drawing the reaction is these two reacting to associate. Um, we said that the R state binds oxygen more tightly. That means that this equilibrium over here should be very large compared to the equilibrium over on the left. Right? So the reaction of the R state binding oxygen should basically shift downward more so. All right, now I'm just going to give these some numbers here. So I'm going to give the T state binding oxygen the label K1. Over here, I'm going to give the R state binding oxygen label K2. And we also have these equilibria here. So I'm going to call this, K3 and K4. All right, it doesn't really matter what numbers you put on which ones. I'm just doing this as an example here. Now, for the reaction going in this direction here, so the T state getting converted to the R state, then binding oxygen, the combined equilibrium constant for that, we take the individual equilibrium constants for each step and multiply them together. Right. Now, the equilibrium going in that direction should be the same as equilibrium going in this direction, because we're starting off in the exact same point with just pure T state, and we're ending up in the same point with R state subunits with oxygen bound. So it doesn't matter which way we go, we're starting off in the same point, ending in the same point. So the energy and therefore equilibrium of the two paths should be identical. So the going down and then to the right path would have an overall equilibrium constant of K1 times K4 here. All right, now what did we say here about the relative magnitudes of K2 and K1? Well, we said K2 is a very big number relative to K1. K1 is small. Well, in order for this equality to then be preserved, K3 has to be small and K4 has to be big, right? Because they have to basically compensate for the differences between K2 and K1. Well, what does this mean then? That means that K4, the equilibrium for the shift of the T state to the R state with an oxygen bound, is bigger than the shift from the T state to the R state without oxygen bound. So this bottom reaction here lies more to the right. So literally with oxygen binding here, because the R state binds oxygen more tightly, this means that once oxygen is bound, the equilibrium for the T and R state has to lie more to the R state with that oxygen bound. It just has to mathematically, thermodynamically. And that is it for question number 8.